All right, so let's continue talking about planes and the concept of the lift, for example, and the Bernoulli's principle, right? But before we go any further, let's ask a question. What is the similarity? Remember in the first couple of weeks, second, third week, we talked about automobiles. We talked about the combustion of fuel, the oxidation of hydrocarbons to create carbon dioxide and water, and the energy that was used to move the cars, right? So what's similar between automobiles and cars? In one sense, they're similar because you're burning a fuel that creates heat and energy, and then it's converted to mechanical energy, right? How do they differ? Well, the first difference is that in automobiles, the combustion occurs in a chamber, right? It pushes the piston and therefore pushes the tires, and therefore you move the car forward. And the kinetic energy that is used to take care of the air resistance on the car. In planes, that also happens, right? You need to be able to move forward. But in addition to that, you need to provide lift. And so the key there is that you need to burn them in such a way that the air will be flowing around the wings in such a way that you'll also have lift. So in one sense, you have forward motion, kinetic energy in both cases, but in the case of plane, you need to have lift. So you need to design the plane in such a way that you'll also have lift. Okay. What is the difference between planes and rockets? And if you've heard about going to the moon, to space, and so forth, right? For planes, the core principle is the Bernoulli principle. That is combustion, the heat that is generated, the conversion of mechanical energy, and then designing the wing in such a way that you actually get lift, right? You design the wing so that you get lift, and the plane can go up and also go forward because of the kinetic energy from the burning of the fuel. In rockets, the key principle is not the Bernoulli's principle, but in Newtonian mechanics, every action has an equal and opposite reaction. You must have heard about, right? And the other important thing with the rockets is that unlike on Earth and say even planes at fairly high altitudes, the oxidizing agent, oxygen, is in the air. So the automobiles and planes, they carry a fuel, but they don't carry their own oxidizer. For rockets, on the other hand, for it to go to the moon or wherever, you need to carry your own oxidizer. It could be liquid oxygen, for example, or some other oxidizer. So that's a key difference, right? The other difference, of course, is that the Newtonian mechanics, it's not that it doesn't use the Bernoulli principle. For example, you can imagine that the space shuttle is trying to land. It lands like a glider, like a plane. So obviously, the Bernoulli's principle is, the wing are designed in such a way that it can land in a controlled fashion. But for the most part, you're looking at Newtonian mechanics principles where the gases that are created and burned in these chambers are expelled with such a high velocity that it propels the rocket in the other direction. So that's the other key difference. And if I'm not mistaken, this could be from our Huntsville, Alabama Space and Rocket Center with a bunch of these Saturn V rockets and other type of rockets. And the key here is that unlike planes, it carries a fuel that is burnt and the oxidizer at the same time. Okay, so the plane, as I said, it flies because of the Bernoulli principle. There's a pressure differential, right? And it turns out that whether we know it or not, we actually use the Bernoulli principle in our daily lives in several different ways. An example I'm showing here is a plunger and a nozzle like this, for example. Imagine you have a plunger, and you plunge this, is essentially air, past this metal tube, right? What happens as you plunge the air really fast across the tube, the pressure at this particular point is just slightly less than the pressure inside. And therefore it pushes the liquid up. And then as the liquid is coming out, then the air is able to push the particles of liquid to wherever you want to go. So what we're actually doing is using the principle that by pushing air at a very fast velocity past a certain location, we are reducing the pressure, thereby actually forcing liquid up a certain tube. So it's a good example of use of Bernoulli's principle. Another one is about boats, and if you remember, I think in week 2, I had this picture of a boat. If you watch sailboats, you wonder. I said, can sailboats go against if the wind is blowing in a given direction? Can the sailboats actually go against the wind, as it were? And the answer is yes. It depends on how you orient the sails in such a way that it can create a differential pressure and then have a net force in the direction that you want to go. And so again, an illustration of the Bernoulli's principle. Now, I'm not a sailor myself, and I don't know how to use the sails, but the idea there is that you allow the wind to flow in such a way that you have a net force going in the direction that you want to go. So the principle is very similar. If you can actually draw these force diagrams and actually show that in some cases, even if the wind is, for example, going in this direction, by adjusting your sails, you can actually make the boat go in a direction that appears to be almost directly against the way the wind is blowing. So it's an application of the Bernoulli's principle too. So it's pretty fascinating. One other application I want to show you as a reminder. And remember, when we're in a plane, we want the plane to be in the air and not on the ground, and keep flying in the air as long as possible, unless we want to come down. If you're driving a car, our objective is to remain on the ground, and particularly with race cars, for example. If you're going really fast with the race car, then you want to make sure that you stick to the ground as opposed to flying all over, right? And so it turns out that there is. I'm sort of really simplifying this whole idea. But race cars, for example, are designed in such a way that they're designed to be very stable, stay close to the ground. And so they sort of think about how do you design the car, automobile, race car in such a way that the air is flowing underneath the car at a very high velocity, for example, and resulting in a net force acting downward to the car, keeping the race car right on the ground as you would want, right? So as it says, air increases the velocity, reduces the pressure, and the atmospheric pressure actually pushes the car on the ground. Now, I'm not sure if you might have seen some cars with some of these stickers in the back, ordinary cars, whether the effect is large enough in an ordinary car. But certainly in a race car, that sort of effect becomes absolutely critical. So what we've done in these two videos is to link up an important concept, an idea called Bernoulli's principle, energy balance, and to how planes fly, and to how, for example, boats are able to go with sails in a direction against the wind. And so I hope we can appreciate it the next time we get on a plane and look at the wings, for example. We can look at how those things are being moved around in such a way. It's to adjust the lift, adjust the direction in which we're moving, and so forth. So I hope that was fun.